Welcome back. And here is another lesson. In this lesson, I'm going to walk you through solving systems of inequalities. And this time, these systems of inequalities are actually more involved: quadratic, linear, quadratic, quadratic. I'm going to do two examples. One will be a quadratic and a linear. The other one would be a quadratic and quadratic, different types. And then we go through each one. First thing that you need to know for this specific question, question number one, is that you need to know everything there is to know about the first equation, the first relationship, and this first relation is hyperbola. Okay, is a hyperbola, and you need to know everything about hyperbola: how to graph it, what is the center, what is the transverse axis, and all the specifics of it. It's specific because you need to graph this freestyle. That's what the question is. Okay, you cannot use the technology because technology will be easy to do. The next one that you need to know is the everything there is to know about lines: how to graph a line, the slopes, y-intercept, plotting points, and drawing. And that's what you need to do. First, you need to recognize that even though this is an inequality, but the original relation is written as x squared minus y squared equal to 9. And this negative in front between the two squared variable of x and y, that's the giveaway sign of being a hyperbola for part of a conic sections, okay? And the center is 0, 0. So this is the original form, standard form of a hyperbola. By the way, there's a squares on each one of them right there. Okay, and in this case, what we have, this is actually the A and B, they're the same, and this represents a rectangular hyperbola. I don't want to get into that, but check out the other videos about hyperbolas, and then you can refresh your memory. So center is 0, 0. We also know that the transverse axis, the length of transverse axis is 6, because of this 9 is 2 times the square root of 9, which will be 6. And we know that because of x is positive and the value of y value is negative, that means that it is a horizontal transverse axis. So this is the horizontal transverse axis. Okay, very good. So we have that information. We can go ahead and graph this now slow, and of course you have to graph few other points, but we can go ahead and graph it. So I have drawn the preliminary sketch of the hyperbola, where we have this rectangular hyperbola with two asymptotes. Remember, there each hyperbola will have two asymptotes that they intersect at 90 degrees, and the equation of the asymptote is basically rise over run. In this case, it's just y equal to x. That's what that is, because y squared is over 1 and x squared is over 1, so 1 over 1 is that, and it's a square root of that, actually a square root of this value here. If you go back to the original AB, it would be B over A. That's the slope of the asymptote. In order to graph this a little bit accurately, we need to have at least 4 other points, and that's very easy because it's just a rectangular hyperbola. So we can easily, and it's symmetrical, always is. So what we can use is the values that you plug in there for x and y. You get 9 based on that operation. Well, points 5 and 4 and any variation of 5 and 4 will work because it's a square. Okay, so in this case I can do 5 and 4. I can also do negative 5 and 4. Okay, and also I can do negative 5 and negative 4 and 5 and negative 5 and negative 4. So all of those values will work when you plug it in. So let's plot those values in. Let's plot all of these coordinates on the graph, and then we can graph the hyperbola as accurately as it can possibly be based on the 5 points. So these are the 4 points plus the vertices of the original hyperbola, which is 3 and negative 3. And now we're going to go ahead and do the line, and that's what you will get. Now let's go ahead and graph the line we have to change the line, which is written in this form, x minus 2y plus 3. We have to change that to the slope-intercept form because it just makes it easier to graph, and then graph that. I'm going to just do the manipulation and then graph it. Pause the video and then double check, and then you can see the result. First, you have to change that to the slope-intercept form, and when you manipulate the equation, you end up getting y equals to 1/2 x plus 3/2. And let's graph this now using the y-intercept 3/2, then the slope half, and you should be able to do that. And when you graph this, you're going to get this line like that after manipulating it and putting in a standard form. And you just use a slope, which is 3/2, and then you go up 1 over 2, up 1 over 2 until you hit these points. And you notice that now you got yourself these points of intersection. So one is this one, the other one is that one. So one point of intersection for the solution to this system is 5, 4, and the next one is -3, 0. So now that we have the point of intersection of this system, the two relations, now we need to go back to that actual inequality and see it in what region there is a common answer or common solution for both. And to do that, we need to do a check, or I call it actually a test point. We got to do a test point, and the easiest one, I'm going to start with 0, 0. Okay, so the right in the center origin, we're going to check this area. If that point 0, 0 works for both, then we're going to shade this area. If it doesn't work for both, then we have to shade the other side of the graph. Okay, so let's plug it in and let's see if it works for both. So we're going to grab this test point 0, 0. We're going to take the test point and we're going to plug it into the system, one inequality at a time. So 0 squared minus 0 squared, is that less than 9? 0 is less than 9? Sure it is. And then the other one is 0 minus 0 plus 3. Is that greater than 0? 3 is greater than 0, so yes it is. So now that we know that that is the solution, we're going to come up here and we're going to shade everything in here as part of the solution. That means all points, infinitely many points, they satisfy this inequality within that region will be part of a solution. And it's very hard to actually write this as an interval notation. That's why this system needs to be solved graphically with a shaded region. Okay, now one important thing to pay attention to is that this system of inequality, in each one, we have the inequality sign and doesn't include equal sign. That means the boundary lines that they create these graphs, they cannot be solid lines. So that's one of the reasons that we have to create this dotted line for hyperbola and a dotted line for the line. What does that mean? It means points on the graph of each of these relations. One is a function, the other one is a relation. The points on the boundary on the graph, they are not part of the solution. That's what it means. If it is an equal sign, if we had an equal sign in either one of them, then one graph would have been a solid line, the other one would have been dotted line. So pay attention to that as well. Okay, here's the next question. And in this case, we have an ellipse and we have a parabola. Okay, let's go ahead and manipulate that. So first one, the ellipse, instead of, we have to divide. So I'm going to rewrite it as a standard equation and ignoring the inequality right now. And then to do that, we have to divide everything by 16 to be able to graph this. Okay, here it is. And now we can graph it. We have a major axis of 8. And then the minor axis is 2, and then center at 0, 0. We're going to go graph that. And then let's deal with the parabola, and that is y. So x squared minus y equals to 2. So y equals to x squared minus 2. Okay, so we have that, and that is easy as well to deal with. We have vertex is 0 minus 2. and congruent to the parent function y equal to x squared. So we can just graph that parabola and graph that ellipse and then see the point of intersection and then deal with the inequality. So let's go ahead and graph. So when you graph this freestyle, this is what you're going to get. So obviously you can see the imperfection there, obviously, but that's okay. We're not using technology. This is a freestyle. I'm using all the information that I had for the ellipse and the parabola, and then I graphed it. Now that I've graphed it, and I kind of noticed that the first the the ellipse is dotted boundary lines because of its less than right here, less than 16, but the parabola is actually a solid line. Okay, that's a solid line. All right, now based on that, we're going to do a test point, and if the test point works, then we shade that region. If it doesn't, we have to shade the outer region within the boundary. So what test point would be the easiest? Well, 0, 0. Let's do that. So here is a test point. I plugged it in for the first ellipse inequality, and then we get, yes, it is true. But the second, look at what happened when I plugged in 0 squared minus 0. Well, 0 is not greater than 2, so that's no. What does that mean? That means that inside of the ellipse is the solution, but outside of the parabola is the solution for the second. So that means we need to shade just outside of the parabola, but inside of the ellipse. That region that you can see. This is the solution, this shaded area, both of them together is the solution to the system. Okay, that's it. I hope you found this useful. Subscribe, like, and share your comments, and hit that notification bell whenever I post a new video. You'll be notified as soon as I do that. Until next time, keep at it.